01B, the search for tetrahedral symmetry in germanium-70. And this actually represents a collaborative work among several institutions, including Ohio Wesleyan, Fulton College, Florida State University, the University of Sao Paulo in Brazil, and Bundesland für Strahlenschutz in Germany. And the speaker today will be Khanh from Ohio Wesleyan.
Hello everyone, my name is Khanh, and this summer I worked with Dr. Heron K on the search for pyramid-like shapes in germanium-70. So as we all know, electrons fill up atomic shells, and once an atomic shell is filled, the atom will reach a stable structure of noble gas. And the same story with nuclear structure. When nucleons, which is proton and neutron, fill up nuclear shells, the nucleus will have stable structure, and it will have the spherical symmetry for the shape. And however, nuclei can also be but also the nuclear shape can be deformed and have different kind of shape, such as an American football shape, or we call it like a prolate shape, or an oblate shape, which looks like a frisbee. However, theory also predicts that if we change a different deformation parameter, we can get a shape that looks like a pyramid or tetrahedral symmetry, which I can show right here. But the theoretical foundation for tetrahedral symmetry is not only based on like the simply looking mathematical model that you guys just saw. It's also based on what we call the calculation of energy shell gap. And this plot shows the proton energy on the y-axis and the deformation parameter on the x-axis. And these lines are the excited state that a proton in nucleus can occupy. And the wider the gap, that the larger the energy, the harder it takes for a proton to jump from one collection of state to another collection of state. Therefore, more than likely, the nucleus will stay stable at the lower lying level. And the nucleus will have a stable shape. And number 28, number 50 are the number of proton and neutron that nucleus should have for spherical symmetry. And the number 32, number 38, number 40, 56, and 58 are assigned to tetrahedral symmetry. And we notice that in germanium-70, it has 32 proton along with 38 neutron. And there's a common gap share between the number 38 gap and 32 gap. Although it is small, we still think that there's a possibility for the existence of tetrahedral symmetry in germanium-70. And theory also gives some experimental signature for tetrahedral symmetry. And what we're looking at right now is the energy level scheme, which is like a fingerprint of a nucleus. These numbers on top of the level bars represent the energy of the excited state of the nucleus. And the number right at the bar represents the spin angular momentum of the energy state. The plus and minus side indicate the parity of the wave function. With plus meaning that we have an even wave function, and minus we have an odd wave function. And these arrows represent the gamma ray, the transition that nucleus will emit when it jumps from one energy state to the lower energy state. And so the experimental signature for tetrahedral band say that tetrahedral band is a negative parity band that has relatively weak transition that changes spin angular momentum by 2, and strong transition that changes spin angular momentum by 1, going from the tetrahedral band to the ground state band. But more importantly, the excited state of the tetrahedral band should have 0 quadruple moments, which is the parameter that measures the distribution of proton within a nucleus. And an experiment was performed at Florida State University in order to produce germanium-70 or iron-30. A beam of oxygen-18 was accelerated up to 50 MeV and matched again the target of manganese-55, and a fusion product, arsenic-73, was produced. And to relax to ground state, it emits light particle. When 1 proton and 2 neutrons was emitted, germanium-70 was produced. But still, it will have a lot of light energy, so it keeps releasing more gamma rays to finally relax to ground state. And those gamma rays were detected by the detector array at FSU. And using those measurements, we enhance our level scheme, and we pick the most reliable one between 2 available for us. And notice that in this level scheme, band number 3 already has some experimental signature of tetrahedral symmetry. It is a negative parity band with relatively weak transition that changes spin angular momentum by 2, and some transition going to the ground state band. So what we still need to do is we need to measure the quadruple moment to make a conclusive statement about the tetrahedral symmetry in germanium-70. And to do that, we measure the lifetime, because from the lifetime we can infer how fast nucleus can transition from one excited state to another excited state. And from that, we can calculate the quadruple moments of the nucleus. And we measure the lifetime using a method called Doppler shift attenuation method. So to understand that method, let me remind you quickly about Doppler shift. So the Doppler shift effect is the shift in frequency due to relative motion between the source and the detector. In our case, the recoil nuclei releasing gamma ray is our source. And what we're looking at is the detector at 35 degrees. And as you can see, since the recoil nuclei is moving toward the detector, we should expect to have a higher shift of frequency, which lead to a higher peak of energy so appears. And in this situation, this is the peak of when the nuclei release, when it's at rest, and when it moves forward, we will have a shape looks like this. And we use a computer simulation to simulate the line shape, in which we can also vary the lifetime of the excited state. And from that, we can choose the best fit curve to our experimental data. And we can also pick out the lifetime measurement for the excited state. So the result, you get the effect the lifetime 24 state, the mean lifetime 8 state, quadruple moment of 7 state within 2 bands. And these red state right here are the state that we measure quadruple moments for in germanium-70. So we also did theoretical calculation for the quadruple moments and plotted together the experimental results and theoretical prediction. And as we can see, there's a big disagreement between our experimental results and theoretical prediction. Theory predicts that the shape of nuclei should change radically at around spin 9 or 10. But in our case, the shape of nuclei of the germanium-70 should stay relatively constant throughout. And we also see disagreement between experimental results and theoretical prediction for band number 3. And more importantly, since all the quadruple moments for the excited state in band number 3, which is our candidate band for tetrahedrosymmetry, are all non-zero, we concluded that there's no tetrahedrosymmetry in our in germanium-70. And so thank you for listening.
Okay, thank you, Khanh. Questions?
One of the slides you were showing some of the results you had two different lifetime measurements, effective and mean lifetimes. I was wondering what the difference between those are.
Oh, so I didn't tell you about this, but in our simulation, first we assume that the state of interest that we measuring the lifetime for immediately produced during the experiment. And but then that's a pretty simple assumption, because at as you can see in the left scheme, and so let's take an example of say number 7. It can also be produced after state number 9 is produced, or it can be followed through this decay scheme. So therefore, more state can also be produced before state number 7, and the effective lifetime only take the assumption that state number 7 minus is produced immediately, while the mean lifetime corrects for what we call the feeding effect from previous parent state. And so the mean lifetime gives us like a good representation of the lifetime of the excited state.
So in short, effective lifetimes don't take into account feeding from higher lying states. Mean lifetimes do.
Okay, thanks.
Any other questions?
Do you have an idea of why there was such a discrepancy between the theory and the experiments on the data you showed?
I really have like no idea, because we got like the experiment result and the theoretical prediction within the end of our research week, and we haven't taken clear look at the two results compared to each other. But there could be many reasons for the discrepancy between the two. It could be that the theoretical model is not completely accurate describing the behavior of germanium-70. It could also be that our measurement have large uncertainty due to contaminant within like the gamma ray measurements, and it affect the lifetime and eventually affect the quadruple moments of the excited state.
So I'll just quickly add that experience suggests that the theoretical model we use works best for nuclei that show more collective behavior, with stronger transition rates and higher quadruple moments. Germanium-70, though, according to Khan's measurements, are showing lower collectivity and smaller quadruple moments, so the model probably just doesn't do as good of a job representing such nuclei. Okay, why don't we thank our speaker again.